L2 Applications Design Challenge was to build the scale horizontal axis wind turbine. There were no mass constraints or need to self-start, but design restrictions arose from an exclusive list of available materials and manufacturing techniques available to us. In this video we will discuss the design, manufacturing and testing phases of the project.
The aim of the application is to create a wind turbine with the highest power coefficient, which is defined as the ratio of power delivered to the total power available. Since the total power available will be constant, the maximum power coefficient is obtained by the maximum power generated. To maximize the power, a larger swept area has to be designed within the constraints of the application. The turbine is constrained to be printed in a 400 mm long, 100 mm deep, and 150 mm high. Therefore, to maximize the swept area, a one-bladed design with the smallest counterweight is to be designed. The aerofoil was first chosen by shortlisting aerofoils online. 3 aerofoils were chosen, which were designed by Selig and Shiger, especially for small wind turbines. We then imported them into Q-Blade for further analysis. The SG6043 was chosen for its high CL and lift-to-drag ratio. Since the local wind velocity differs along the span of the wing, the proportional circulation and hence lift produced are different. To obtain a constant value, the chord length was reduced as the distance from the center increases. A Schmidt distribution was used for the chord length. The wind direction also differs along the blade, so a twist angle is also applied.
The primary concern for the structure was a possibility for blade failing radially at high speeds due to the centripetal forces, as well as axial and tangential deflections due to the lift and drag of the blade. Assuming that the vast majority of the lift generated by the blade would be generated near the tip, and that the lift far exceeded the drag, allowed the blade to be modelled as a simplified beam of uniform varying thickness. While simplistic, the model resulted in a rough, if pessimistic, estimate of the load distribution of the blade. Combining the load distribution and material properties allowed us to calculate whether the blade would fail during the test and adjust the design accordingly. For the final design, a similar model was used, except that the blade was split into several smaller trapezoid sections, with lift estimates calculated at the boundaries.
Given the counterweight, mass and volume requirements, the nose cone was designed to minimize drag. Having researched the performance of different shape profiles at the test Mach number, it was decided to use the Hack series shape. In particular, LV Hack shape was used, as this minimizes drag for a given volume. The nose was initially designed as a solid plastic revolve with the counterweight side hollowed out in order to add extra mass. However, it was found that this would not suffice the weight requirements, and as such, the design was revised to have approximately half of the cone be made of aluminium and act as the hub. The 2 halves were to be secured by 2 pins which ran along the hub's length.
The common theme among various shapes of counterweight design was that aluminium alone will not provide enough weight. Hence, the final design was an aluminium half cone with blind holes drilled from the base towards the tip to allow heavier materials to be inserted. High tensile steel grub screws were weighted and converted into Creo models before finalizing the design.
Using the coordinate reference shown, we calculated that the center of gravity for the original design would balance the blade.
Chord distribution and twist distribution, along with the chosen aerofoil profile, were implemented into Creo, and the blade was produced. The blade then was connected to the plastic hub. High-quality inspections were carried out by the aerodynamic crew to ensure that the leading and trailing edges, blade tip, and the region where it connects to the plastic hub are as much as smooth as possible in order to reduce the drag. The model then was inputted into a 3D printer and printed out in ABS plastic. Finally, the waviness and the roughness on the blade surface were sanded out to ensure smooth airflow around the blade.
The manufacturing process of the counterweight was simple after a Creo model was made. Feature cam was used to extract all design features. These design features were then programmed into the CNC lathe and milling machines. A block of aluminium was measured and the surfaces were flattened by a CNC milling machine for accurate positioning of the piece. holes were drilled on the block according to the Creo model. Another aluminium half-cone with the shape of the plastic half-cone was manufactured for machining purposes. The two halves were pinned together to prevent unbalanced spinning during the profiling process inside the CNC lathe machine. The final step after CNC machining processes was to clean up the metal swaths stuck inside the holes manually so that grub screws could be inserted.
Despite multiple efforts to fully clean these holes out, they couldn't all be cleaned. Then came testing. We attempted to measure the balance by placing the turbine on a sharp point and evaluating its tendency to fall off balance by inspection. It was found that the blade was not perfectly balanced. Due to debris buildup, the holes were effectively shorter than anticipated, as the grub screws could not fit all the way down. We then modelled this offset in Creo to assess its effect on our turbine, and it was found that this offset the CG in the y-axis by approximately 5mm, which was enough to cause the instability.
Following the blade's failure to balance properly, it was obvious that some adjustment had to be made to rectify the problem. After discussions with the project supervisor in the workshop, it was agreed that some minor adjustments would have to be made to correct the balance, while remaining faithful to the original design. In the revised design, we decided to place the CG above where we wanted it, to allow more flexibility in the vertical location of the CG through the use of grub screws.
The revised design features two M10 bolts drilled into the aluminium hub opposite the blade to ensure that the turbine is balanced about its central axis. In this configuration, it could be tested in the wind tunnel. The turbine was allowed to spin freely at a wind speed of 6 meters per second and was then exerted to a controlled deceleration, where torque and RPM were measured. The procedure was repeated for a wind speed of 8 meters per second. At higher wind speeds, the turbine experienced significant vibrations. Although it was statically balanced, the counterweight did not balance the lift force and created extra drag, resulting in an aerodynamic imbalance. Consequently, the test could not be conducted at 10 or 12 meters per second. Unfortunately, the vibrations hit the resonant frequency of the test rig before the peak of the power curve was reached. Even efforts to stabilize the wind tunnel floor could not mitigate this effect. To test the turbine at higher speeds, it would have to be balanced dynamically. A maximum power output of 46 watts was achieved at 8 meters per second with a tip-speed ratio of 9.86. However, due to the resonance effects, the power curve for 8 meters per second could not reach its maximum, and the best power coefficient of 1.61 was obtained at 6 meters per second with a TSR of 12.56. This is almost 60% above our design TSR of 8. However, one must bear in mind that the turbine was designed to produce its maximum power at 12 meters per second, and the graph of power coefficient against tip-speed ratio shows that the TSR at which the peak of the power curve is reached tends to decrease with higher wind speeds.
After the revised design, the blade was balanced in the rotor direction, but it wasn't balanced in the axial direction properly. In order to avoid all these numerous studdings and holes, if we can design the hub with the steel alloy, it will be very effective and quicker design. One more other way that we could reduce the weight of the counterweight by having a lighter blade. Designing the blade with a honeycomb structure will reduce the weight considerably. Our root section is very big, so it causes a large amount of drag and might lead to the stall tendency. Since we are not required to design a self-starting blade, we should consider reducing the root sectional area to improve the blade performance.
The mass of a 3D printed component is never consistent, and as such, an optimal engineering design would take account for this by having the counterweight be manually adjustable post-production.
Our one-bladed design, which incorporates the counterweight within the nose cone, was an innovative and original idea. Unfortunately, it could not be implemented successfully with the available materials due to unforeseen manufacturing difficulties. In its slightly modified configuration, the wind turbine could not reach its design speed and TSR due to dynamic effects which would have been hard to predict. Nonetheless, it produced a comparatively high power output and therefore achieved its main design goal.